Okay, great. Thanks all for coming to another Compass seminar. Today we have Hanna Miličević. Hanna Miličević is visiting us from University of Zagreb. She's originally from Bosnia and Herzegovina, and she got her bachelor's of engineering, right? From University of Zagreb in civil engineering in 2018, and her master's also in civil engineering in 2020. And she's currently a third-year PhD student in civil engineering, specifically in the water research department at University of Zagreb. This is her first long-form seminar besides her bachelor's and thesis, bachelor's and master's defenses. And Hannah's favorite things about Miami are that her brother lives in Miami, so she gets to visit him. Miami's climate and the energy of the city, and opportunities to connect with people in the similar field as hers. All right, Hanna, take it away. And mention your title because I forgot mine.
Thank you for introducing me to everyone. Once again, my name is Hanna and I'm a PhD student at Faculty of Civil Engineering, University of Zagreb in Croatia. The topic of my presentation today, or rather the title of my future doctoral dissertation, is the effects of submerged sill geometry on the morphodynamics of artificial beaches. Since there is one more year left for the research and formation of the dissertation topic, I will present to you the progress of the research so far and some results, as well as goals that are aimed to be achieved in the end. My presentation consists of introduction about Croatian coast and problems it faces, literature review about previous research and conclusions that serve as a basis for further investigation of dissertation topic, methodology of the research conducted so far and some results, as well as planned future work and objectives. The Croatian eastern coast of the Adriatic Sea, which stretches over 6,000 kilometers, is a region of great biodiversity and historical importance that has been attracting tourists for centuries with its unique gravel beaches. A large number of islands and beaches are the main assets of Croatia's tourist offering. Given that Croatia heavily relies on the tourism as a key economic sector, special attention should be paid to the sea and coastal areas. Growing tourist demand for beach capacity has led to the construction of artificial beaches, mainly pocket gravel beaches, without optimal design parameters being precisely known, such as beach profile, slope, grain size and shape, correct choice of coastal hydraulic structures and their geometry to adequately resist the numerous natural and human influences to which Adriatic coast is exposed daily. Influences such as precipitation, sea changes, wind waves and sea currents are referred to as natural influences, while construction of coastal hydraulic structures such as breakwaters, groins or submerged sill and maintenance such as nourishment and mechanical relocation of material are human influences. These influences lead to morphological changes in the beach such as sediment transport and increasing need for maintenance and renourishment. In the period from 2015 to 2019, Croatia invested about 6 million euros, which corresponds to 200,000 cubic meters of beach material which arose during the winter months. It is assumed that successive nourishment tried to compensate for the loss of beach material during storm events, resulting in a reduction of beach surface, which naturally affect individuals' town tourist offer and increases the overall cost of beach maintenance. On an annual level, an increase in costs was observed. The significant increase in costs and volumes that occurred in 2018 makes it difficult to draw conclusions about the trend. Conclusions about the trend. Dredging the sand material from the seabed there are two reconstructions of two big special beaches in 2018, and this is partly responsible for the increase in 2018, and dredging the sand from the seabed increased overall costs, while river gravel was mainly used in other beaches. The movement of material is generally divided into longshore sediment transport and cross-shore sediment transport, which includes erosion and accumulation processes in these directions. The volume of eroded material is equal to amount of accumulated material if there is no external sinks or sources that would disturb this balance. However, irreversible loss of material can occur in the case of stronger waves or abrasion processes, as well as in the case of freshwater springs, so-called vrulja, that push material into greater areas. On the left side, we can observe video recording from our pilot beach Ploče the day after situation with strong waves and heavy rainfall. We can observe material displacement such as erosion and accumulation, as well as freshwater springs. On the right side, in the figure, which was not taken at the same time, we can observe the effect of freshwater springs pushing material to greater depths. While natural gravel beaches experience periods with milder wave conditions following intense wave activity, allowing previously eroded material to be redeposited back onto the beach face, artificially nourished gravel beaches are at the risk of permanent material loss. For these reasons, it is crucial to investigate the optimal construction methods for artificial gravel beaches to ensure the reduction of material loss and the need for nourishment. It is therefore necessary to identify the most vulnerable parts of the coastline and to establish the temporally and spatially most appropriate monitoring plan for morphological changes on the beach in order to collect data essential for long-term study of beach behavior. The main directions of sediment movement caused by before-mentioned human and natural influences can be easily and cost-effectively tracked with technologically advanced coastal monitoring systems. Coastal monitoring systems based on photogrammetry, video monitoring systems, or drones enables the creation of high-resolution 3D model of the beach and tracking of morphological changes. In addition to that, using these techniques also provide clearer picture of advantages or disadvantages of constructed hydraulic structures, including their geometry and position, which contribute to the behavior of the beach. Coastmap application and video monitoring systems were used to track the evolution of artificial gravel pocket beach in Croatia, and these results helped us to get an orientation for further investigation into the beach behavior of, in general, artificial Croatian beaches. In addition to various field measurement methods, scientists are currently focused on developing a numerical model designed to simulate one-dimensional profile of gravel beach for cross-shore sediment transport. The most significant morphodynamic models are based on wave numerical models, from which it is possible to obtain temporal and spatial distribution of water particle velocities. Temporal and spatial morphodynamics such as erosion and accumulation of gravel particles based on this data are calculated on cross-shore along the cross-shore profiles. At the center of scientific research is the open source numerical model X-Beach Gravel, which with location-based calibration enables the establishment of stable profiles. More details about description of the model can be found in the article of McCall in the references. For this study, we will use X-Beach Gravel for morphodynamic assessments of beach behavior and analyzing the optimal geometry of submerged sill. The open source numerical model X-Beach gravel was selected because it was developed for simulating storm-induced changes on gravel beaches and has already been used in previous studies on changes on gravel beaches. And the biggest disadvantage of other computational fluid dynamic models is computational time. We always try to find the balance between accurate description and adequate computational time. There is an accepted conceptual model in which the morphodynamic response of gravel barriers is related to the relationship between hydrodynamic forcing and beach geometry. An increase in relative forcing conditions leads to morphological changes in the beach, such as berm formation, beach erosion, changes in barrier crest buildup or crest lowering, or changes in the entire barrier rollover. On the artificial gravel beaches in Croatia, where the maximum significant wave height doesn't exceed 3 meters, the responses of beaches A, B, and C occur most frequently, while others occur very rarely or not at all. Similar research, but focus on sandy beaches, was conducted by Bell and Sorensen, who through laboratory conditions demonstrated the effectiveness of beach construction with submerged sill in reducing material transport caused by wind waves. This study included monitoring the formation of the berm or material accumulation and beach erosion. In this study and Dins and Gonzalez study, the most important parameters related affecting the amount of displaced sand material and dynamic equilibrium of beach profile are toe structure depth and crest depth. These results indicate that submerged structure causes larger waves to break and dissipate much of their energy before reaching the beach face. However, these geometric parameters will be also used in our study, but for gravel beaches, as gravel has completely different permeability than sand. Due to such morphological changes, promenades, homes, and recreational facilities along the beach can be at risk. In some cases, damage can lead to significant economic, ecological, and recreational losses. A commonly used solution to these problems are periodic beach nourishment without an appropriate environmental impact study or appropriate post-maintenance, and construction of hydraulic structures. The figure shows the consequences of inadequate nourishment in various Croatian cities. Examples of the use of poor quality building material to fill and nourish the beach have come to the attention of the public. Material with an increased content of clay and silt is used, which has completely unfavorable effect due to marine biocenosis and due to process of sedimentation. Examples of the coastal hydraulic structures include various types of breakwaters and groins. Groins are useful in preventing irreversible loss of material along the beach, but they have a little effect in preventing irreversible loss of material to the sea, often caused by storm events. Research so far has shown that constructing a submerged sill has been beneficial in providing the protection of the beach by reducing wave energy and material loss without affecting appearance of the beach and space for recreational facilities. However, few studies have focused on precisely defining the most suitable geometric parameters of submerged sill for artificial gravel beaches. Such construction could reduce material displacement and prevent beach erosion and consequently reduce maintenance costs. Although the primary purpose of the submerged sill is to create and maintain a balanced beach profile depending on sill geometry, particularly on the depth of sill's crest, it can also reduce wave energy by inducing wave breaking and decreasing wave runup. Submerged sills, along with before mentioned advantages are also considered beneficial for preserving existing plant and animal habitats and for increasing biodiversity, such as creating habitats for seagrass, shellfish and corals that improve water quality. By gaining a valuable insight into finding the right solution for hydraulic sill placement, including key geometric variables such as crest depth, or structure depth, or distance from the shoreline, its impact will be tested on artificial gravel beach in Croatia to achieve the previously mentioned benefits. Extensive field measurements began at the end of 2020 on the artificial gravel beach Ploče in the northwestern part of the city of Rijeka. The field measurements include geodetic monitoring using drones and traditional geodetic surveying. The result of geodetic monitoring is a 3D model of the beach for each field surveys, which these measurements allow us to visualize changes in the beach's surface caused by material displacement. In addition to field measurements, numerical modeling is also used with before mentioned X-beach gravel model. After the model is calibrated on the west coast and validated on the east coast, it will provide prediction of beach profiles under wave influence. In this way, our aim is to investigate a morphodynamic response of artificial beaches to wave action and to create an engineering tool that can be used in the planning of new beaches and in assessment of the nourishment need of existing beaches. As I previously mentioned, in addition to erosion, berm formation is the most common type of beach response to various natural influences, since X-beach gravel model was originally developed for simulating the impact of storm events on the morphodynamic response of natural beaches at significant wave heights of 5 meters and higher. Relatively few simulations and model validations have been conducted for artificial gravel beaches. Such studies are especially rare in closed seas, where the maximum significant wave heights are lower and storm events are weaker compared to open sea and natural beaches. Field measurements necessary for calibrating X-beach gravel model were obtained from our colleagues involved in joint project called BeachX project. For each completed survey, detailed point cloud of the entire beach surface was created, from which cross-sectional beach profiles can be easily extracted into AutoCAD. And these field measurements results will be used to compare to those from numerical model. Our focus is artificial gravel beach Ploče, the largest beach complex in the city of Rijeka. The beach was built over 2 existing natural inlets and is protected by 3 groins extending from existing headlands. The central groin divides the beach into 2 parts, the western part and the eastern part, and both of which are about 130 meters wide. However, the beach is heavily eroded by storm events every fall and winter, and these storm events are the main drivers of morphological processes on the beach. The topographical data of beach changes were collected using SPM photogrammetry over a period of 1 year by Geodetic Institute Rijeka and Faculty of Civil Engineering in Rijeka. From January 2020 to February 2021, the Ploče beach was surveyed 19 times outside the summer season and mainly after storm events in parallel with wave measurements. The incoming waves were measured using wave buoy located 2.5 kilometers southeast of the Ploče beach. The tidal and wave boundary conditions for our model were derived from the nearest tide gauge called Bakar. For proper calibration, 5 field surveys focusing on 3 significant storm events were selected. These events were selected because most of visible berms formed after them. The first event due to shortest period between 2 topographical surveys, only 1 day. The second event as one of the most severe storm events with high significant wave height, and the third event with milder wave conditions but with a clear crusher sediment transport. It is important to note that one-dimensionality of X-beach gravel model limits its ability to simulate longshore sediment transport processes. Therefore, we selected profiles that minimize the impact of longshore sediment transport gradient during storm events. For each crusher profile, on the western and the eastern part of the beach, the difference between eroded and accumulated area before and after storm event were calculated. In the case of crusher sediment transport, the difference should ideally be 0 or close to 0. On the western part of the beach, the crusher sediment transport occurred between profiles 2 to 6, while on the eastern part of the beach, for model validation, it occurred between profiles 4 to 8. Other profiles were not considered due to influence of seawall and groins, which causes longshore sediment transport, making them unsuitable for modeling with X-beach gravel model. For proper calibration and validation of the model, a series of tests with different morphological parameters and parameters that describe sediment characteristics have to be conducted. The three most important model parameters related to sediment transport are coefficient of inertia, angle of repose, and sediment transport coefficient. If sufficient data are available, these parameters can be calibrated for each gravel beach to accurately represent crusher profile changes. Following previous research by Bogovac and McCall, the planned testing values for sediment transport coefficient are 0.5, 1, and 3. For coefficient of inertia, 0.5, 1, and 2. The angle of repose will be tested on 35, 45, and 55 degrees. The key parameters describing sediment characteristics include hydraulic conductivity and the median grain size, and these parameters will be set based on suggestions of previous studies on the Ploče beach. It is planned to conduct 36 different combinations to test the model sensitivity to sediment transport parameters and its ability to predict the position of displaced material. The most significant correlation with beach profile changes was observed with variation in the sediment transport coefficient and angle of repose, while the combination with inertia coefficient didn't show any dominant influence on profile changes.
Hanna? This median grain size D50, obviously you can set whatever you want in the model, but for the beach, how do you measure that? Do you measure
does range from
a bunch of rocks,
yes,
and then you
from 16 to 32 millimeters? I think that is range. That is some average value of sediment on our beach. Our aim is to find the best combination to describe berm formation and beach erosion, which are common on Croatian artificial beaches, to assess the quality of our model predictions compared to actual measurements. We use Breyer-Skill score, standard for coastal modeling. According to Van Ryn's classifications, values above 0.6 indicate good model predictions. More details on calculating BSS value can be found in our article on the slide. All of storm events we investigated are characterized of formation of berms. During these storm events, existing berms were eroded and new berms were created higher on the beach profile. The figure shows that the X-beach gravel model can qualitatively reproduce observed changes for both light and heavy storms. Different storm severities required different conditions. In quantitative terms, model can underestimate the volume of the berm. This suggests that site-specific calibration of model parameters related to sediment transport, such as angle of repose and sediment transport coefficient, may affect the accuracy of the model predictions. For significant wave heights of 1.6 meters or less, the best fit is achieved with the angle of repose of 55 degrees and sediment transport coefficient of 0.5. For significant wave heights greater than 1.6 meters, the optimal parameters are angle of repose of 35 degrees and sediment transport coefficient of 3. Despite the need for site-specific calibration, overall skill of the model prediction is reasonable with an average Breyer skill score of 0.8 for selected parameters. According to OneRine's classification, these results range from good to excellent, but these results are only preliminary as we intend to study behavior of more storm events than are shown in this graph. Further testing will focus on the relationship between the geometry of submerged sill and the movement of material under different wave conditions. Such structure has two main objectives: to protect the beach from erosive wave action and to minimize material loss. Previous studies have shown that the depth of Sill's crest has the greatest impact on morphological response of the beach. The primary parameters planned for model testing include significant wave height, peak wave period, wave steepness, crest depth, and tow structure depth. The test will use real wave parameters from storm situation in Croatia and will start by simulating beach profiles without submerged sill. Later, these results will be compared to those from tests on coastal profile with same geometry and same wave climate, but with submerged sill. The total change in the beach surface or material displacement is calculated in the relation to the initially defined profile with and without the sill. This approach will provide insight into beach behavior both with and without submerged sill under different wave influence. And additionally, the test will examine whether the construction of submerged sill reduces wave run-up on the beach face, which could consequently reduce material transport. The orange line presents model profile and the blue line presents initial profile, and we can observe the amount of displaced material with and without submerged sill under equal wave conditions. The smaller the ratio between material displacement with sill and without the sill, the greater the efficiency, and the aim is to obtain as little displacement as possible. This study will also focus on the effect of varying the depth of sill crest on sediment movement. The figure shows crusher profile with same geometry but with different crest depths of 1.5, 2 and 2.5 meters. The test will aim to identify changes in the gravel beach profiles and determine the optimal position of the crest, meaning the location that results in the least material displacement. The test will be also carried out for other geometric conditions such as changes in tow structure depth and beach profile slope. Ultimately, based on obtained data, we aim to refine recommendations related to design of artificial gravel beaches, especially for application in Croatia and similar Adriatic location, and to identify design strategies that minimize maintenance costs, such as mechanical sediment transport and nourishment, while ensuring the long-term stability and functionality of the beach. Thank you for your attention.
Thank you so much, Hanna. I learned a lot. Are there any questions for Hanna in the room first?
Yeah.
Susan first, then Brad.
What are the sediments in natural beaches in Croatia?
Sorry, I didn't understand you.
So your presentation covered artificial gravel
yes.
beaches. So what is the sediment on the beaches, the natural Croatian beaches? Is
It is the same sediment, but that is these beaches are artificially nourished, it is like technical maintenance that is not natural beach that is for hotel purposes to grow, to expand the capacity of our beaches for tourists and everything, because now we don't have beaches, too much beaches to cover all tourists that came in Croatia, because it's very famous touristic place.
So more or less, it's the same.
Yes, it is same sediment. Yes.
Okay.
And if I may add, besides those, there's a lot of just rocky. There's a lot of like large rock coastlines that people can still use, but these gravel beaches are kind of bigger community beaches.
Yes, and artificial beaches behave differently as natural beaches.
Right.
Are there trade-offs between how you manage for mundane conditions, ordinary waves, versus extreme events? If you build a thing that'll protect against an extreme event, does it also, operate in a different way on the day-to-day, year in and year out waves? If you protect against huge erosion events, are you also preventing some beach building activities that might happen in other conditions? Are there a lot of trade-offs, or is it kind of just you think there's one right answer to how deep your sill should be?
This is only about erosion and accumulation and berm formation on the beach. It is only research about that.
Right. Is it driven by preventing big disasters, or about maintenance little maintenance over time?
Our biggest storm event is about significant wave height of 3 meters, but that is big for Croatia. That is not big in general for, I don't know, here or somewhere else, but that's why I said that we investigated for wave conditions similar to Adriatic Sea. That is the most significant, the largest significant wave height is 3 meters.
And are those always bad for beaches, or are they sometimes good for beaches, these big events? 3 meter events?
Always bad for beaches, yes, always bad for beaches. For artificial beaches, because natural beaches can do it by yourself, can erode and this. Sorry.
Yeah.
I have a question. So it seems to me that if you're choosing the size of your of the sediment, let's say on one end of the extreme you have sand, you can make sandy beaches, but my intuition is that sandy beaches erode more easily. But also to many people, sandy beaches may be more attractive. Now this is a personal thing. Some people like gravel beaches, some people like rocky beaches. And you can go to the other end of the extreme and just have large rocks. There are such beaches too. At some point somebody had to decide, okay, we'll make these kinds of gravel beaches. Has anybody ever done kind of a retrospective cost/reward analysis of the optimal sediment size that attracts most people and minimizes the maintenance cost?
Unfortunately, no, because we need to have a law about it. It is called Barcelona Convention. It is about the protection of Mediterranean Sea against pollution and everything about the coast and maintenance of the coast. But unfortunately, no, we are not good in laws and everything. So it is problem in the general of Croatia. Everything is too slow to resolve, especially for the coast and these problems like this.
All right. Are there any questions from Zoom?
No.
No questions from Zoom audience? All right, thank you, Hanna.
Thank you very much.